I'm erasing this part, and we will start off with what the reaction looks like. So first we will see how the reaction looks like. So the reaction is basically, we will substitute an electrophile. We will have an electrophile. This will be our reagent. Electrophile will be our reagent, which will react upon our substrate. Now, what will be our substrate? As is evident from this name, it will be an aromatic compound, and most like in your syllabus of JEE Advanced as well as NEET, we have only EAS over benzene ring. So we will have a benzene ring or a substituted benzene ring, which we will talk about in the later half of this class. So our substrate will be either benzene or a substituted benzene, and our electrophile will be our reagent, and the electrophile will be substituted over one carbon atom of the benzene. So this will be our product obtained. Now, why is this called a substitution reaction? The very first doubt, that how is it substitution? It looks like as if it's an addition, because electrophile is something which has a positive charge, which is philic about electrons. That's why it's called electrophile. So if E plus is our electrophile, then this looks like as if this is being added over here, but no. If we observe very keenly, here we have a hydrogen bonded. In every carbon, we have a hydrogen bonded over here in all the carbons. So it's basically the replacement of CH bond by a CE bond. It's basically the replacement. It's basically the replacement or substitution of CH bond by a CE bond. CE bond. E is our electrophile. Okay. So that's the basic definition of what an electrophilic aromatic substitution is. If this is clear, then we will move on to the mechanism of electrophilic aromatic substitution reactions. Okay, so erasing this part. So talking about the mechanism, it is a two-step process. It is a two-step process. The step 1 of this reaction mechanism is, say we have this benzene ring. A benzene ring is a conjugated cyclohexene, conjugated cyclohexane. So we have conjugated pi bonds like this. This is what a benzene looks like. Now we have an electrophile. Now this electrophile in your questions will directly not be stated as E plus. It will be some reagent, which I will be talking about after going through the mechanism. Okay, so let's assume for now the electrophile coming in is E plus. So if E plus is our electrophile, just a second. Okay. So if E plus is our electrophile, then if we observe very keenly, this pi bond has more number of electrons compared to a sigma bond. So the pi electrons will attack on this electrophile. Now, how will this attack? When this pi bond will break, it will create a negative sign on one carbon and a positive sign on the other carbon. Actually, this doesn't take place, but in order to understand, we can assume it is taking place. Like if a bond breaks, then one side gets a negative charge, the other side gets a positive charge. In case of a benzene, it's actually symmetric over both the sides and over any pi bond. So on breaking of pi bond, we can either assign a negative or a positive to any of the carbons. So I've assigned a negative at the top and a positive at the bottom. Now this negative charged carbon has more electron density because it's negatively charged as compared to this carbon atom over here. So this electrophile will be attracted to this carbon, and this electrophile will be attached at this carbon at this place. So we will not draw this plus minus when we will show the mechanism officially. We will just show that this pi bond is attacking at this electrophile, and by the means of the mechanism that I just now explained, these two pi bonds remain intact, and this electrophile joins over at this point, leaving a carbocation over here, because this, we said, as this pi bond breaks, it will create a negative and a positive charge. So the negative charge, so the point at which the negative charge was found, the electrophile being positive came here and attacked, and this E got attached over here. However, the other carbon which has the positive charge, that remains as it is. So this is basically a carbocation intermediate. This is basically a carbocation intermediate, and this is not just a carbocation intermediate, it is one of the most stable carbocation intermediates you will study in your entire organic chemistry. This carbocation intermediate is, as you can, oh sorry, my bad. Okay. So this carbocation intermediate is resonance stabilized. As you can observe, this we have a charge sigma pi conjugation. So this plus charge will be resonating throughout this structure. So this resonated, this conjugated carbocation, we can call this as a conjugated carbocation, because the system is conjugated, pi sigma pi and charge, sigma and charge. So this is entirely in a conjugation. So this plus charge can move, like if it resonates, then if you see, if you find its resonance structures, we will see that if this pi bond breaks like this will be negative, this side will be positive. So negative positive will form a bond. So this bond will come over here. This bond will come over here. This charge will be gone. These charges will be gone, and the carbocation has now shifted over here. Similarly, another resonance, this bond breaks like this. This bond breaks like this. Again, resonance takes place, and this plus charge can move over the entire ring. So that's why this conjugated carbocation is very much stable in nature, and due to resonance delocalization. So I'm writing here that this is stable due to resonance delocalization of the positive charge. Delocalization of what? Of plus charge. As we are very much aware that in chemistry, anything which happens due to increase in stability. So if we have a charge at particular carbon, if the charge is localized, that means it cannot move to any other place inside the compound, inside the same compound, then it is not as stable as compared to a delocalized site where the charge can be moving around across many carbons, so thereby decreasing the charge density on each carbon. Okay, so we have a stable, a resonance stable conjugated carbocation over here, and this is called this has a name. This is known as the Wieland intermediate. This intermediate has a name called the Wieland intermediate. So this, whatever I have discussed over here, I can just go through it once more. So we have a benzene ring, an electrophile comes in. Electrophile has a positive charge. Benzene ring has 3 conjugated pi bonds. Pi bonds have excess of electrons. Any pi bond, here all the pi bonds are equal. Here there is no other group present in the benzene ring. When there would be some other groups, then the things would be difficult, and the things we will study in the next part of the class. But here the entire benzene ring is symmetrical. So all the pi bonds are identical basically in terms of the electron density it carries. So any pi bond can attack at the electrophile gets attached, leaving a carbocation at one spot. However, I have resonated the carbocation to this place, so I'm not putting this plus sign over here again. So yeah, then this carbocation form is a conjugated carbocation, which is known as the Wieland intermediate, which is much more stable due to resonance delocalization of the plus charge. Okay, the plus charge can be resonance delocalized over here. So that was the step 1 of this process, and this step is also the rate determining step of the reaction. We often see in JEE Advanced and other good examinations, we are asked about the RDS steps. So we must be acquainted with the RDS steps of all reaction mechanisms included in our syllabus. So here, this step is the rate determining step of this reaction. This is the slowest step as well. This is the slowest step. We already know that the slowest step is always the rate determining step of this reaction. Also, I would like to put up one point, which is a conceptual one. If you observe that this benzene initially was aromatic in nature, this was an aromatic compound, right? However, when the electrophile comes and gets attached here, this intermediate formed is stable due to conjugation. I already wrote that. However, it is not aromatic anymore, right? So if it is not aromatic anymore by the Debye rules, by the Huckel's rule, so we know that a non-aromatic substance formed from an aromatic substance is not a feasible reaction at all. In chemistry, we always move towards increasing stability. However, in this step, we can observe that a comparatively lesser stable intermediate is being formed from a stabler reactant, yes, or a substrate. So an aromatic substance is getting converted to a non-aromatic substance. So if this is happening, then we must understand that this process is endothermic in nature. That's why the energy of the intermediate, that's why we often see that the energy of intermediate, what energy am I talking about? The potential energy basically. The potential energy of the intermediate is always much greater than the potential energy of reactant as well as the product. Okay. Because product formed, as we will see in the next step, step 2, will be again aromatic in nature. So we will regain the aromaticity in this electrophilic substitution mechanism. However, the intermediate is non-aromatic, therefore it has a much higher energy than that of the reactants and products. So this was one important thing I needed to get over here. If this is clear, then we will move on to the next page. So now we have step 3 and step 2. So that was our rate determining step and the most important one. Step 2. As we had observed that we had this Wieland intermediate already formed, just redrawing it. This was the Wieland intermediate already formed. So this Wieland intermediate now is non-aromatic in nature, as I have already said. But however, the initial reactant was aromatic. So aromatic to non-aromatic is a non-feasible reaction. So we need to regain aromaticity in this process. So how to regain the aromaticity? If we look carefully, that this carbon over here is sp3 hybridized, isn't it? So this carbon is sp3 hybridized. That means it should have 4 sigma bonds, if not a lone pair. Carbon doesn't have a lone pair. So of course it should have 4 sigma bonds. We can observe 3 sigma bonds connected to it. 1 is to E, 2 is to carbon atoms adjacent. But where is the 4th one? The 4th one has a hydrogen connected to it, of course. That's pretty obvious. So what we will do is, we will eliminate this hydrogen. I mean, this sigma bond has 2 electrons over here, this shared pair of electrons. It will leave the shared pair of electrons and remove itself as H+. So we will remove H+. As we remove H+, these electron pairs remain over here. So it induces a negative charge at this point. So negative charge is induced at this point. Now again, negative and positive. Again, this negative and positive charges on the adjacent atoms of carbon reconstitute this pi bond. But now with the E attached. So if we observe that again from a non-aromatic substance, by the elimination of the this ion, the H+ ion, we have obtained again aromaticity. Again we have got an aromatic as well as electrophile substituted product, right? Because we were going to substitute an electrophile. That was our main focus in this particular reaction, that we need to substitute an electrophile to this benzene ring. So we have been successfully able to do so by the help of these 2 steps of this reaction. So aromatic as well as electrophile attached. Okay. So again, we can observe that this is a non-aromatic to aromatic, so it's a very much highly feasible process. So it's a highly exothermic process. It will be highly exothermic or a feasible process. From the accounts of thermodynamics, we know this will be a highly exothermic process. Okay. So that's all about this mechanism of this reaction. I think that's all about it. I'll just say one more point about it, that if we want to draw, like these questions sometimes come up in the good examinations, that drawing of potential energy versus reaction coordinate graph. This is sometimes we will also observe in books, like in good books like MS Chauhan and stuff. There are too many questions in every reaction mechanism they teach in 11th and 12th. There are some questions regarding to this particular topic, that drawing P versus reaction coordinate graph. So I will talk about it a little bit regarding this reaction. So how to draw this? So if we have to draw the potential energy versus reaction coordinate graph, we will have potential energy in the y-axis and the reaction coordinates in the x-axis. If we observe in the previous page, we go on to the previous page, we observe that this initial reactant was an aromatic benzene. It was basically benzene. It was an aromatic compound. Okay. But the intermediate found was Wieland intermediate, which was, although it was conjugated carbocation, but it was less stable than an aromatic, because aromaticity is the first and foremost condition for checking stability of carbocations. So if we observe over here, let us assume that this was the energy level of the reactant. Okay, let's say R. Okay, so this was the reactant over here. In the first step of the reaction, it was an endothermic reaction or a non-feasible one, as we moved from an aromatic to a non-aromatic structure. So from an aromatic to a non-aromatic structure, we move like this. So our graph goes up. Why does it go up? Because the intermediate must have higher energy than the reactants and products. That's the point I explained in the previous page. So the intermediate, this is the intermediate. This is what? This is the intermediate. I'm naming it as I. So the intermediate has higher potential energy as compared to the reactant, right? And it has the maximum potential energy, in fact. So this is our first step. However, when this is formed, so this particular step is our first step, and this is called the rate determining step of this reaction. Also, this step requires the highest amount of energy that needs to be delivered from outside, from our side. So this energy can be calculated by calculating this particular part. If we see this part, this is known as the activation energy. This is known as the activation energy required for the RDS. Required for the RDS to take place. So this RDS can be taken place by giving this activation energy. This is represented by this symbol E with a suffix of capital A. So this activation energy, we will study about activation energy in greater detail when we study chemical kinetics and physical chemistry. However, basically this is the amount of energy that is needed to provide us, that we need to provide in order to convert the reactant to the unstable intermediate. Now, after this first step is over, the next step, the step 2 is after the slow step, this RDS is over, the step 2 is a fast step. This is the fast step. This is a fast step, and this is an exothermic step in nature. So, if it's an exothermic step, we know for an exothermic step, we are moving from a non-aromatic substance to an aromatic substance again. Pay attention. So, non-aromatic to aromatic substance means stability is increasing. So, if stability is increasing this side, energy is decreasing, right? Potential energy and stability are inversely related to each other. One compound which has higher energy has lower stability, and which has lower amount of potential energy, it has higher stability. So, as we are moving from non-aromatic to aromatic, our stability is increasing. Stability is increasing. However, our energy, which is potential energy, that must be decreasing. So, the energy is decreasing. That means if I have to draw the graph for the next step, the graph will look like this. Finally, it overs here. So, here we see in this part, this was the RDS, step 1, this was the step 2. This is the fast step of this reaction. So, this is how the potential energy versus potential energy versus reaction coordinate graphs looks like. We have 2 steps, 1 step, second step. So, it's a 2-step process. The number of peaks equal to the number of steps. We can write it over here. Number of peaks equal to number of stages or steps. Okay. One intermediate is formed, which is a carbocation intermediate, which is the Wheeland intermediate. So, yeah, that's about it. And also, number of peaks is number of steps. However, if in between the carbocation rearranges, not about the Wheeland intermediate, I am not talking about the Wheeland intermediate, I am talking about the reagent. In the first page, if I say this reagent E+, this is not always given as E+. If this reagent becomes a carbocation also, so then carbocation can always rearrange. We know rearrangement of carbocation has no constraints in any reaction anywhere. If a carbocation is being formed and there is some other carbocation possible which has more stability and lesser energy, then always rearrangement takes place. So if this becomes a carbocation, in fact, in case I'm talking about, so if this becomes a carbocation and if this can rearrange itself, then it will of course rearrange. In that case, our potential energy graph will have a slight change. The number of peaks will increase. There will be another peak indulged in between these fast and the RDS steps. The highest peak will always be the RDS, which is the formation of the Wheeland intermediate. After that, if there are any subsequent peaks, they will be either for the fast step, which is the last peak, and any subsequent in between will be due to the rearrangement of carbocations in the intermediate steps. I will explain it to you by forms of a question in the next slide. So I think this should be clear till here. Yeah, that's about the mechanism and how it goes. Okay. Also, this step is the basically gain of aromaticity. It's known as the gain of aromaticity. The first step was the loss of aromaticity, and the second step is the gain of aromaticity. Okay. So this is clear. We will move on to the next page. Okay. Let's see about the reagents. Let's talk about the reagents. That what reagents will come in your paper which can give you an electrophile. and which can cause the electrophilic aromatic substitution to take place. So the reagents which are commonly used, I am talking about a few, there are many, there are too many. We will be talking about every reagent in detail. However, the main important reagents are number one, if we are given with some halogen molecule X2, where X is either chlorine or bromine, why not fluorine or iodine is because fluorine is highly explosive in nature and iodine is too stable to react very fast, so its yield is very less. Chlorine bromine gives considerable amount of yield. That's why we mainly take chlorine and bromine in case of halogens. So X2 in the presence of AlX3, aluminium halide, or it can be AlX3 or it can be FeX3 as well. Are these two same? These two are not same, but their properties are same. Why are they same? Because both of them are what? They are Lewis acids. They are Lewis acids. I mean, their octet is not filled. If we draw the covalent nature, if we draw the covalent form of this is like this. We see the aluminium. We have one X over here. We have one X over here. We have one X over here. It has 6 electrons, as we can see. 1, 2, 3, 4, 5, 6 in its last shell. But it needs 8, so its octet is not complete. However, it does not have any extra space as well, so it will not take any coordinated species. However, it will act as a Lewis acid. That means it has a lack of electrons in its outermost shell. So if it acts as a Lewis acid, then why are we taking Lewis acids over here? Why are we taking Lewis acids over here? Let's see. What it will do is, basically, when X2 will react with, suppose I am saying with AlX3, AlX3 being Lewis acid in nature, it needs electrons. It needs electrons. What is it does not only need electron, it can take any electronegative substance. Anything which has a negative charge has an excess of electrons. So it will be showing affinity towards all such substances. So X2 when reacts with AlX3, AlX3 will come and take away 1X, forming AlX4 minus. This complex will be formed and this will lead to the formation of X plus. Now as we can observe, X is a halogen. Halogens have high electronegativity. They are high En substances in periodic table. Now having high electronegativity, it is not very much pleased to get a plus charge on itself. So this is unstable. So this is very unstable. Okay. If our reagent is unstable, our reaction will take place faster. So this X plus is formed as an electrophile. This will act as a electrophile over here. Okay. So now if we have a benzene ring and if we write over here X2 in the presence of AlX, okay, the action of FeX3 is exactly same. It will form FeX4 minus and X plus. Okay. We'll take it as AlX3. Then this will give X plus, which will get attached to any place over here, because for a non-substituted benzene, there is no difference between any particular position. We'll have this X. This will be our product. So this is a halobenzene, right? So halobenzene will be formed. If this is clear, this was about our first reagent. Now we move to the next one. Perhaps a very important one I'm going to talk about. This is basically Rx in the presence of, again, any Lewis acid. This Lewis acid can be AlX3 or FeX3 or anything, like there are many. So okay. So Rx, what is Rx? Rx, R is a alkyl group, we already know, and X is a halogen. So it's basically an alkyl halide, right? We have an alkyl halide along with a Lewis acid. Action is exactly the same as we have shown in the halogen case. So how will it act? Let's see. Suppose we have this Rx, this reacts, AlX3 comes, it being a Lewis acid, it takes away this X, so this becomes R plus and AlX4 minus again. So again, the action of AlX3 was just to take away this X and form the carbocation. So often questions come that what was the action of, like, why had we taken this Lewis acid over here? The action of Lewis acid is, its action is to lead to the formation of electrophile. to form the electrophile ALX3 or Lewis acid is being used. So this electrophile here is R plus. Now what is R plus? R plus is a carbocation, as we all know. So this is a carbocation, right? So this carbocation is our new electrophile, which will be reacting on our benzene ring this time. We have this benzene ring over here. We have Rx and ALX3. So this will form R plus, and this R plus will go and combine with this benzene ring according to the EAS mechanism, which I have clearly mentioned in the previous slides, to form this. Okay, so this is basically an alkyl benzene formed, right? Things are pretty simple till here. This reaction has a name in itself. From here onwards in your physics, chemistry, name reaction start. So this is basically named as the Friedel-Crafts alkylation reaction. Okay, one of the most important reactions in your entire syllabus, Friedel-Crafts alkylation. This is how it takes place. Now let's talk about one question. Let's take up one question. Suppose we have a benzene ring and we are going to have this as our reagent. So this is an Rx, as you can observe, and this is a Lewis acid taken in together. Okay, and this is our substrate, which is our benzene ring. So we have to perform EAS reaction in this particular question. So how to perform? Pretty simple. It's same as I have shown in the previous slides. So let's do it. We have the reagent, which is this, plus FeCl3. FeCl3 will come and take away this chlorine atom as the chlorine ion. So we'll be left with Cc plus. Writing it in a better way. This is basically what? C. We have C. Of course, this is CH2. This is CH3. So this is basically ethyl carbocation here. So ethyl carbocation is left behind along with FeCl4 minus. Okay. Now this is our electrophile form. As we can observe, this plus sign means electrophile. So now it's pretty easy. This benzene ring is present at any position. As we have said, benzene ring is identical right now till now. So this plus sign will come here, and like this electrophile gets attached. So this gets attached like this. We can attach it in any particular position. So I'm just showing it like this. This C plus comes over here. We get the structure like this. That's our answer in this particular case. That was very simple. Let's move on to a better question. Okay. It looks similar to the previous one. This question also looks similar to the previous one. Anybody watching this video, I would request them to try this question on their own. But this has a little bit of punch in this particular question, because I had mentioned one point while teaching the part of potential energy diagram that when you draw this diagram, there can be subsequent peaks in this diagram. So the subsequent peaks always mean carbocations. What carbocation? Which carbocation? Valent intermediate is itself stable. It does not rearrange anymore because it's resonance stabilized. But if a carbocation is being formed as an electrophile, in that case, there must be or might be, in fact, cases of rearrangement taking place. So for that, we have to find that whether this question is one of them or not. Let's solve it. Let's see. So first thing which we should do is, we have this, the chlorine atom, reacted with AlCl3. AlCl3 will come and take away this chlorine ion as Cl minus. Like the same thing, we have the plus sign over here, CCC. This is basically a propyl carbocation, and we have this AlCl4 minus along with it, right? Now, I've seen many students who perform the same thing which I've taught in the previous slides. What they do is they take this carbocation and they say, yeah, this is an electrophile. This is our electrophile over here. It will straight away get connected over here. So they make this blunder. Why am I calling it a blunder? You understand this? Because this is not the correct answer. As soon as you do this, you will get a -5 basically. So this is not the correct answer. Why is that not the correct answer? Because this carbocation formed over here is not the stablest form of it. It's not in its stablest form. Why? Because there is rearrangements possible in this carbocation. So we'll do here, we'll say that this, it can rearrange itself. If it can rearrange itself, how will it rearrange itself? Let's see. We have this carbocation like this. Now, this particular carbocation is a 1 degree carbocation. Why? Because this carbon is connected to only a single carbon over here. This is a what? This is a 1 degree carbocation. However, we have hydrogen over here, 2 hydrogens over here, right? These hydrogen atoms can be removed as hydride ions, and this plus charge can be rearranged to this particular spot. So we will say by 1,3 hydride shift, of rearrangement of carbocations, we observe this hydride will be shifted and it comes to this position. I'm just let me draw it really. So one hydrogen is removed as a hydride from this position and shifted to this position. As a result, this carbocation gets shifted to this particular position back. So we get a carbocation which is a 2 degree carbocation. Now, from the basic principles of hyperconjugation, we already know that a 2 degree carbocation is much more stable than a 1 degree carbocation. So this process is a feasible process. It's a feasible process. What is the meaning of feasible? Anything which is easily possible in chemistry is feasible process. Okay. So it has, basically we can say it has del G less than 0. It has a negative delta G. So it's a feasible process. So if it is a feasible process, then it will take place no matter what happens. If it has the chance, if the carbocation gets a chance to rearrange itself and form a more stable form of itself, it will always do so. So it rearranges to a 2 degree carbocation, and now this 2 degree carbocation is our new electrophile. This will be our new electrophile, and this will go and get attached to this particular benzene ring, which I will show in the next page probably. So now let's see, this was our benzene ring over here connected to this. We had this carbocation, this newly formed carbocation over here. Okay. This carbocation now comes and gets attached. So this is our correct answer. So it should be clear to everyone why this is our correct answer and not this. This is wrong. Why this is wrong? Because this carbocation can rearrange itself. It was not in its most stable version. So it can rearrange itself. So if it can rearrange itself, it can either rearrange by hydride shift or by methyl shift, alkyl shift, or by phenyl shift. So we know rearrangement. If we talk about the rearrangement, then first process, this is the priority order I'm writing down, okay? So from top to bottom, the priority goes. First, we will check for hydride shift. That is, if there is a corresponding hydrogen atom present in the adjacent carbon or not. So we will check for hydride shift. The second thing we will check for is alkyl shift. So alkyl shift, alkyl can be methyl, ethyl, anything. If there is an alkyl group, we can also shift it. It's an alkyl shift, or which is the third one is the last one is the phenyl shift. If there is the benzene ring, we can also shift the phenyl ring. We will see this phenyl shift phenomena in the pinacol-pinacolone rearrangements, which we will do in E1 mechanism. Okay. So there we will see how phenyl shift takes place and we obtain particular stable carbocations by this as well. So this is the rearrangement of carbocation. You have to mind it. You have to keep this thing in mind. And yeah, that's the priority order from top to bottom. First you will check for hydride, then alkyl, then phenyl. So that's the reason why this is the correct answer. Now I'm just reverting back to the point of potential energy graph. What I said over there was just I just said it theoretically. Now let's prove it. So we had this PE graph with the reaction coordinates over here in this side, with the potential energy in this side. This was our reactant, and we moved like this. This was our first step. This was our carbocation. This was our RDS, rate determining step. And after this rate determining step, there was this slow step taking place, right? So before the slow step, in this for this particular reaction, there are 3 steps. Why? There will be an intermediate. Okay, the peak will be a bit less. Peak will be not as much as this. The peak will be lesser, and then it will move down a bit more than this point. I will be explaining these parts, and then after that, finally, we have the fast step. This is the fast step. So this is the final product. This is the product. This is the reactant. This is the carbocation. First carbocation. This is the rearranged carbocation. So I'm writing RC plus. Okay, and this is the fast step. This was the RDS or the slow step. This is the correct graph over here for the potential energy diagram. Okay. So students might have that confusion that we know only there are 2 steps in the reaction, so there will be only 2 peaks. However, this particular peak is for the rearrangement of the carbocation in the previous page. This particular step corresponds to this subsequent peak. So now I'll say one thing, that why this carbocation has a lower value as compared to the other one, because this second rearranged carbocation is a 2-degree carbocation, while the first carbocation found was a 1-degree one. So it has more stability than the first found carbocation. So if it has more stability, then it will have less energy. We know always potential energy is inversely proportional to stability. You have to remember this until you crack your examination, whatever you are aspiring for. It's a very important point. So potential energy of any compound is inversely proportional to its stability. So if RC plus is more stable, if I compare stability of RC plus, we will get RC plus is more stable than C plus, okay, as I have named over here. Then if we compare the energy, the order will be reversed, of course. The energy of C plus will be higher than that of RC plus. And that's what I have shown here in this particular graph. The energy of C plus, which corresponds to this level, is much higher than the energy of the RC plus, which corresponds to a lower level. Okay. So that was the PE graph for this particular reaction. And this was about Friedel-Crafts alkylation reaction. I think everything should be clear by this question. We can try one more question. I'll not do it over here. You can take it as, whoever watching this can take it as a homework or something. Suppose we have this benzene ring. Have this. This can be done in the same way. This is also a question of Friedel-Crafts alkylation process only. So yeah, anybody wishing can copy this down. It will be done in the same way as I have done the previous one. Okay. So coming to my last topic for today, it's the Friedel-Crafts acylation process. It's another named reaction. These are the 2 named reactions present in your syllabus for this particular class 11th EAS part. So how does this take place? The reaction looks like we have this benzene ring, or the substituted benzene, as we will be discussing in the next classes. If we have RCOX, this is our substrate. This is our acyl chloride, acyl halide. X is a halogen, it's chlorine or bromine. So this is called an acyl halide. Why acyl? This RCO group itself is called acyl. This is called the acyl group. This has the name, it's called the acyl group. So that's why this becomes acyl halide, acyl chloride or acyl bromide. So that's why it comes acylation process. So it's pretty much evident that the acyl group will be connected to the benzene ring from the name as well. So let's see what happens. Final product is basically this acyl group connected to the benzene ring. So this is formed. This is basically a ketone, because C double bond O and R carbon connected to both sides is a ketonic group. This is a ketonic group. So this is a ketone, but this is a phenyl ketone, because there is a benzene ring connected to one arm of the ketone. This is the phenyl ketone. Okay. So phenyl ketone is formed as a result of this Friedel-Crafts acylation process. The process mechanism goes in the same way, but I have to just say it once. So let's see. We have this RCOX, and we have Lewis acid along with it. Okay, I forgot to mention, my bad. I forgot to mention the Lewis acid over here, which will help in formation of the electrophile. Other than Lewis acid, our electrophile will not be formed. That's the main thing. So we'll also have AlCl3 or FeCl3 X3. Okay. That's our Lewis acid. That's very important. Okay. So we have this AlX3, suppose. Okay. So this AlX3 will again come and take away this X minus to leave the acyl carbocation, right? This acylic carbocation. This acyl carbocation is formed along with AlX4 negative. This acyl carbocation is our electrophile, and this electrophile gets connected to the benzene ring. So we get this phenyl ketone as a product. So that's our product. This is about our Friedel-Crafts acylation process. One very important doubt that must be going on in some of my viewers' brains, that is, will here also carbocation is formed. This plus is on the carbon itself, so this is a carbocation. So there must be carbocation rearrangement case just as Friedel-Crafts alkylation, right? But no, there is no carbocation rearrangement which can take place in this particular process. Why? I will explain that to you. So I'm explaining it in this side. Writing, no rearrangement takes place in this case because suppose we have this R, C double bond O, and we have this positive sign over here. Now suppose this R is something where we can resonate or we can form any rearrangement. If we have to resonate, suppose if this was another some conjugated thing, suppose let's, for an example, take this R as, or let's take it as anything like this. Suppose there's a ring, so we have a pi bond over here. Suppose there's a pi bond over here. So can this rearrange? Can this rearrange? No, it will not rearrange. Why? Because if it rearranges, that means this carbocation will move over here. This bond will break like this. The negative charge comes here. So the pi bond will be formed over here. So this carbocation will be eliminated. So I mean, let's rearrange and show it properly. What I'm saying is, if suppose this rearranges, if I rearrange, suppose assuming that it does, so let's see what it looks like. So it looks like this, plus as this moves this side, okay, this bond breaks, the negative positive bond forms over here. We have C, we have double bond O. This is something which is formed. Okay, even if this is more stable than this particular carbocation, why? This carbocation had oxygen connected to itself. Oxygen is highly electronegative. This carbon is sp2 hybridized. It has electronegativity. So it is the sp2 hybridized, and again oxygen is connected to it. Oxygen being an electronegative atom already is pulling electrons, so it is unstable. I'm accepting this point. This is stabler, but this is not feasible. Why this process is not feasible? Because this carbon has two pi bonds I mean, this carbon has 2 pi bonds. That means this carbon is demanding sp hybridization. Is this clear? We see in carbon dioxide C double bond O double bond O, that is sp hybridization, right? So sp hybridization means a linear structure. A linear structure means a 180-degree bond angle. That is what is the demand of this situation. But however, this was an sp2 hybridized state. So this already was at a 120-degree bond angle and it is demanding sp hybridization. However, but we know resonance is not a true phenomena, it's a hypothetical phenomena. So the hybridization cannot change like this. We cannot form an sp carbon over here. So being an sp2 hybridized carbon at a bond angle 120-degree, this structure is demands of sp hybridization. A bond angle of 180 degrees is the demand. So the angle strain is very high. It has a very high angle strain. So due to this very high angle strain, because of the delta theta is approximately how much? 60 degrees. Because it's at 120-degree bond angle, but it's demanding 180-degree. But we cannot change the hybridization from sp2 to sp because it's a resonance phenomena. Resonance is a hypothetical phenomena, right? So we cannot do that. So in that case, the delta theta is so high that this resonance structure is very unstable. This is very, very unstable. Okay, due to high angular strain at this particular site. So being very, very unstable, this cannot be feasible. So we cannot rearrange or resonate this particular carbocation. So that's the concept about why no rearrangement can take place in this particular case. So no rearrangement takes place, and as I have stated over here, directly this RCO plus gets attached to this particular benzene ring to form the phenyl ketone as our final product. So that was about Friedel-Crafts acylation as well, and this concept should be clear. This is something good and maybe asked in some good examinations. So that was all from my side today. Thank you. It is good.
sp2 যেটা বললে ক্লাস 11 এর স্টুডেন্ট মানে ব্যান্ড অ্যাঙ্গেল কনসেপ্টগুলো কি আগে ক্লাস
11 বন্ডিং পড়ানো হয়েছে 4th চ্যাপ্টার,
মানে এগুলো কি
আগে পড়িয়ে দেওয়া হয়েছে।
ওই ফিজিক্যাল কেমিস্ট্রিতে পড়িয়ে দেওয়া হয়েছে,
ফিজিক্যাল
তারপর
কেমিস্ট্রি,
অর্গানিকে
ফিজিক্যালে না ইনঅর্গানিকে পড়ানো।
ইনঅর্গানিক
আমি যদি মানে টাইম পাই আমি সব বুঝিয়ে দেবো।
লাস্টের দিকে পড়ানো হয় না 11
আমার অ্যাকচুয়ালি অর্গানিকটা একটু বেশি স্ট্রং বলে আমি অর্গানিকটাকেই অ্যাজ আ ডেমো নিয়েছি। কিছু ইম্পর্টেন্ট কনসেপ্ট আমি সেই জন্যই দেওয়ার চেষ্টা করেছি।
এখন যে স্টুডেন্টগুলো আছে তারা 11 তারা কিন্তু অনেকেই বুঝবে না।
না, আই থিংক
শুরু করতে হবে তো বন্ডিং থেকে।
বন্ডিং নয়, প্রথম চ্যাপ্টার থেকে মূল কনসেপ্ট, তারপরে অ্যাটমিক স্ট্রাকচার, তারপর পিরিয়ডিক টেবিল, তারপরে বন্ডিং, তারপরে গ্যাস স্টেট।
ঠিক আছে,
অর্গানিক তো লাস্ট পার্টে আসছে। অ্যাকচুয়ালি এটা